Hello everyone, welcome to the JCE Connect online lecture series. In the today's lecture, we are going to discuss the first topic in the module number 4, that is discrete time Fourier transform. And in this particular lecture, I will be covering up the definition of discrete time Fourier transform and some of the properties of DTFT. And in the previous module, that is module number 3, we discussed a similar kind of transformation technique which is from time domain to frequency domain known as the Fourier series. The major difference between the Fourier series and Fourier transform is the Fourier series is applicable to only a periodic signal, which means the signal which is having the infinite duration. But whereas the Fourier transform is a tool which is used to convert the signal which is in time domain into the frequency domain signal. And based on the nature of the signal, we classify the Fourier transform into the discrete time Fourier transform, which is DTFT, and continuous time Fourier transform, which is known as CTFT. And both are applicable. They are restricted for only a non-periodic signal which is of finite duration. And in our syllabus, we have only discrete time Fourier transform, means which is used to convert the discrete time signal which is in time domain into the corresponding frequency domain representation of the same discrete time signal. So now let us see the basic definition for this non-periodic discrete time signal in terms of its Fourier transform. So please clear with the Fourier transform is a tool or a transformation technique to convert the any signal which is in time domain into a frequency domain. Therefore, it is a frequency domain representation of the time domain signal, whether it is continuous time signal or discrete time signal. If it is continuous, then it is known as continuous time Fourier transform CTFT, and the signal is a discrete one, then it is known as discrete time Fourier transform, which is DTFT. Now coming to the definition here, a non-periodic discrete time signal x of n is given by the equation x of n is equal to 1 divided by 2 pi integration from minus pi to plus pi x of e raised to j omega into e raised to j omega n into d omega. Right? Where x of e raised to j omega is given by the equation in summation form, which is n varies from minus infinity to plus infinity, the time domain signal x of n multiplied by e raised to, now it is minus j omega n. The first equation is known as the synthesis equation, and the equation number 2 is known as analysis equation, where x of e raised to j omega is the DTFT of the signal x of n. In the last module we discussed, that is a continuous time Fourier series for continuous time signal x of t, and its CTFT is given by x of k, right, using integration. And these x of n as well as x of e raised to j omega is known as the DTFT phase. They both forms a DTFT fair. X of e raised to j omega is a frequency domain representation of the time domain signal x of n, and it is also known as the spectrum of x of n. Spectrum means what? It is a frequency representation of the given signal x of n. That's why x of e raised to j omega is also known as the spectrum of x of n, right? And if you take the magnitude, you will get the magnitude spectrum of x of n, right? And if you take the tan inverse of imaginary divided by a real part of the complex number, if the DFT value is a complex number, if you take the tan inverse of imaginary part divided by real part, then you will get the phase value of that particular the segment x of n. And please remember that x of e raised to j omega, that is the DTFT of some sequence, is always periodic with fundamental period 2 pi. That is x of e raised to j omega plus 2 pi. This omega is what? It is a frequency, discrete frequency. Even over 2 pi fundamental frequency, you will get the same, the spectrum signal x of e raised to j omega. So this is about, we have here the synthesis equation x of n and the analysis equation x of e raised to j omega. This equation number 2 is very important. Henceforth, for any discussion of properties of DTFT, we will be using this analysis equation, that is x of e raised to j omega in summation form, right? So equation 2 is very important. Okay. So now coming to the sum of the properties of DTFT, like the same property we discussed for CTFS, that is continuous time Fourier series. So we have similar kind of properties for DTFT also, right? So the technique, the idea, the logic remains same, only the representation is different, right? So the first property coming is the linearity, right? So what is the linearity, right? So when there is a weighted sum of the two input signals, then the output of the system is the weighted sum of the individual response, the weighted sum of the individual responses of the two input signals, right? So here the system transformation we used is the DTFT, right? If the discrete time Fourier transform of x of n is given by x of e raised to j omega, similarly DTFT of y of n is given by y of e raised to j omega, then the weighted sum of these two input signals, right, a of x of n plus b into y of n, is given by the signal z of n. So z of n is the weighted signal, weighted sum signal. Then its DTFT is given by z of e raised to j omega is equal to the DTFT of individual inputs, sum of DTFT of individual inputs, that is a into DTFT of x of n is x of e raised to j omega plus b into DTFT of y of n is y of e raised to j omega, right? So now let us prove this one, right? So let us begin with the DTFT of the individual inputs. So the DTFT of x of n is given by this equation using synthesis equation, n is equal to minus infinity to infinity x of n e raised to minus j omega n. Similarly, we write for y of n, DTFT of y of n, which is given by y of e raised to j omega. Now what we have to prove is, when z of n is the weighted sum of these two input signals, its DTFT z of e raised to j omega is equal to the weighted sum of DTFT of these individual inputs, right? So for that, let me write z of e raised to j omega is the DTFT of z of n, which is given by this equation. Let me substitute z of n from this statement. Z of n is equal to a into x of n plus b into y of n multiplied by this e raised to minus j omega n, right? So here, after simplifying this, so a is constant, we'll take outside a summation, this x of n into e raised to minus j omega n I will write first, plus b second constant I will write before the outside the summation or before the summation, and then summation minus infinity to infinity, the second input signal y of n, which is multiplied by e raised to minus j omega n, right? And we know that by using the RHS of these two equations, that is summation x of n e raised to minus j omega n is given by x of e raised to j omega, and summation y of n e raised to minus j omega n is given by y of e raised to j omega, right? So by using the RHS of these two equations, we can write z of e raised to j omega is equal to a into x of e raised to j omega plus b into y of e raised to j omega, right? So this is the expected the proof of this linearity. Coming to the second property, the time shift, right? So if the original signal x of n and its DTFT is given by x of e raised to j omega, if I consider some shift in the time domain signal, right? So x of n is the time domain signal. So if I consider some shift n naught, which is considered to be a signal yn, so y of n is equal to the input signal with some shift, that is n naught amount, x of n minus n naught. So when some time shift is considered in the input signal, what is its DTFT? So that is given by y of e raised to j omega is equal to the DTFT of the input signal, original signal x of e raised to j omega, which is multiplied by e raised to minus j omega and n naught. And what is this n naught? The n naught is the time shift added in the signal x of n. So now let us prove this one. So again we'll consider x of e raised to j omega, which is a basic DTFT definition as we all know. And similarly, since we have to prove y of e raised to j omega, so we shall write the equation for y of e raised to j omega, and the input is y of n, of course. And this y of n is, it is the time shifted version of the signal x of n, that is x of n minus n naught into e raised to minus j omega into n, right? So now let me substitute in order to get the desired proof. So we have to simplify by substituting n minus n naught is equal to some variable m, right? So when n minus n naught is equal to m, so we have to write for, since it is e raised to minus j omega n, so we have to modify it in terms of n. So n becomes m plus n naught. So summation n minus infinity to infinity. So x of n minus n naught becomes m. So x of m e raised to minus j omega, and this n becomes what? M plus n naught, right? You just simplify this exponential signal x of n e raised to minus j omega m into e raised to minus j omega n naught, right? Look at the signal here, x of n, which is a function of m, right? Means we have to combine this signal x of m with the exponential, which is having the m term. So out of these two exponential signal, which is having m term? The first one, right? And the second exponential term becomes what? It is independent of m, so we'll take outside the summation. So that is taken here, summation minus infinity to infinity x of m e raised to minus j omega m, right? And by looking at this expression, we can write, which is a, in place of just n, we have m. So therefore, we can consider this as the DTFT of input signal x of n, which is given by x of e raised to j omega multiplied by this e raised to minus j omega n naught, right? So in this property we discuss, when we shift the signal in time domain by some unit, what is its DTFT, right? So now in the next property, we'll see the frequency shift. Frequency shift means after doing what modification in the input signal, you will get a shift in the frequency domain, right? So x of n is what? The signal in time domain. X of e raised to j omega means, which is a frequency domain signal, right? The signal in the frequency domain, right? So frequency shift means you have to shift the frequency content in this signal. You have to perform the shifting operation in the G, right? So here it is omega is there. So now let us shift this omega by some unit, say beta, right? So to do this, what modification I have to do in the LHS side, right? So uh, let us multiply the input signal x of n by e raised to j beta into n, right? So that when you multiply the signal x of n by e raised to j beta n, at the output side or RHS, your frequency omega will get shifted by omega minus beta, right? So if you multiply 2 here, right, in place of b, beta, if you write 2, then at the output in the DTFT you will get x of e raised to j omega minus 2. So beta value can be either, it can be positive or negative also. So now let me prove this one. X of e raised to j omega, this is again the basic definition of DFT. And similarly, we'll define y of e raised to j omega. And then you substitute y of n. So what is y of n? E raised to j beta n x of n, that, right? So we'll keep x of n first and we'll combine both the exponential terms, right? So e raised to minus j, omega n is common, so it becomes omega minus beta here, right? So now you can compare here, right? So this equation, right, with the first equation, this x of e raised to j omega, understood? So in place of uh, omega, what we have is omega minus beta, right? That's why it can be written as x of e raised to j omega minus beta, that is equal to y of e raised to j omega. And next property is the scaling. It is also known as time scaling, means you are scaling the time, that is an independent variable of the signal. If x DTFT of x of n is x of e raised to j omega, if I scale the signal, if I time scale the signal, that is x of p into n, right? This p is what? The scaling value, which should be greater than 1. P should be greater than 1. And the time scaled signal is given by z of n. And what is its DTFT? So its DTFT is given by z of e raised to j omega is equal to, see the DTFT here, x of e raised to j, it is omega by p, omega divided by p, right? Then the input n is multiplied p here in the output omega is divided by p. So that is a simple logic you can remember, right, during the scaling. So now let us prove this one. As it is x of e raised to j omega is there. Now z of n, its DTFT is z of e raised to j omega summation minus infinity to infinity z of n e raised to minus j omega into n. So now let me substitute z of n. So what is z of n? X of p n, which is a time scale signal. X of p into n e raised to minus j omega n into n. So now for the further simplification, let me substitute Pn is equal to m, so that n becomes m divided by p, right? So summation n is equal to minus infinity to plus infinity. Pn is equal to m, so it becomes x of m e raised to minus j omega. N is what? M divided by p, right? So that is x of m e raised to minus j. Now let us combine this p with omega. So this becomes omega by p. The same thing can be written as omega by p into m, right? So now in place of omega, what we have is omega by p, right? So this can be written as x of e raised to j omega by p. That is equal to e raised to j omega is equal to this. This is the required proof we want, right? So in the next video lecture, we'll be discussing the few more remaining properties of this DTFT.